This is Laplace transforms, and in this video, we'll be talking about the definition of a Laplace transform. So let's go ahead and look at this definition here. So here we have f of t is a function on 0 to infinity. So the Laplace transform of f is the function capital F defined by this integral. And it is equal to, so f of s is equal to the integral from 0 to infinity of e to the negative st power multiplied by the function f of t dt. Now, the domain of f of s is all the values of s for which the integral exists. And the Laplace transform of f is denoted by both capital F and the scripted L of f. So we're going to jump right in and we're going to use this definition of the Laplace transform to find the Laplace transform of the function f of t equals t squared. So for s greater than 0, we're going to use the definition of a Laplace transform. So the Laplace transform of t squared of s is equal to the integral from 0 to infinity of e to the negative st t squared dt. And there we have improper integral. So we'll take the limit as n approaches infinity from 0 to n of e to the negative 2t t squared dt. And that is going to be equal to the limit as n approaches infinity. And here we'll have integration by parts. So we will let u equal t squared and dv equal e to the negative st dt. du is 2t, 2t. And v is equal to negative 1 over s e to the negative st. So let's go ahead and fill this in. So that would be uv. So we'll have the opposite of t squared, e to the negative st all over s. And we will stop and evaluate that from 0 to n. And of course, we still have this limit. And then we have minus the integral from 0 to n of v du. So that would make this a plus. And now we would have 2 over s, and we can actually put that on the outside of the integral. So 2 over s. And then we have t e to the negative st dt. Okay, so continuing in the same fashion, we'll have the limit as n approaches infinity. So we have negative n squared e to the negative. Let's go ahead and just keep this. And now we have another integration by parts. And here we have u equals t, du is dt, dv is going to be e to the negative 7t dt. And here we have v is negative 1 over s e to the negative st. So going ahead and filling that in, we would have negative te to the negative st all over s So there's our uv minus, and we stop and evaluate that from 0 to n. Minus the integral, and we can make that a plus of v du, so we have e to the negative s t all over s dt. Of course, we still have this limit, so now we have the limit as n approaches infinity, and now all of these are going to be evaluated from 0 to n, and I will also factor out an e to the negative st, and now we will have negative t squared over s, and we will evaluate that from 0 to n, and then we have a negative 2t over s squared. And now, taking this next integral, we will have a negative 2 over s cubed. And then all of this will be evaluated from 0 to n. So now we have the limit as n approaches infinity, and we have e to the negative sn, and now we have negative n squared over s minus 2n over s squared minus 2 over s cubed. So that's plugging n in, and then of course we have minus plugging in a 0, and that will give us a positive 2 over s cubed. And actually this should, now we're plugging in a 0 into that, so we would have minus an e to the negative sn, all but the last term is equal to 0, plugging in a 0. And here, and that should be, we don't even need that. Plugging in a 0, we would just have a positive 2 over s cubed. And if we take the limit as n approaches infinity, of course, this whole term goes to 0, and our limit is 2 over s cubed. Okay, let's take a look at our next example. Determine the Laplace transform of the function f of t equals t e to the 3t. So we're going to have the Laplace transform of t e to the 3t of s, and that's equal to the integral from 0 to infinity of e to the negative st multiplied by our function te to the 3t dt. And that is equal to the integral from 0 to infinity of t e, and let's go ahead and combine those exponents. We have 3 minus s multiplied by t. Let me just fix that, 3t dt. And now, of course, we have our improper integral, so we will have that this is equal to the limit as n approaches infinity of the integral from 0 to n of t e to the 3 minus s multiplied by t dt. And so now we have, and this time I'll use the tabular method for parts. So we have t, 1, and 0, e to the 3 minus st, 1 divided by 3 minus s, e to the 3 minus st, and then we have 1 divided by 3 minus s squared, multiplied by e to the 3 minus s to the t. And so we have the limit as n approaches infinity of, let's go ahead and factor that e to the 3 minus st out, and we have that multiplied by 1 over 3 minus s minus 1 over 3 minus s squared. And there, we will evaluate that from 0 to n. Okay, so we have the limit as n approaches infinity, and we'll go ahead and put our n in there. So we have e to the 3 minus s multiplied by n, multiplied by 1 over 3 minus s minus 1 over 3 minus s squared minus, I can see that I made a little error here, and so this will be an n minus, of course our exponential term is 1, this term will go to 0, so this would be a plus 1 over 3 minus s all squared. We have that limit as n approaches infinity and so as you can see, we will just have 1 over 3 minus s all squared. If you'd like, we could just write that as 1 over s minus 3 all squared. Okay. In this next problem, we will be referring to the table of integrals for the integration. And let's go ahead and determine the Laplace transform of the function f of t equals the cosine of bt. Of course, b is a constant, so we will have the Laplace transform of the cosine of bt of s, and that's by definition the integral from 0 to infinity of e to the st cosine of bt dt. And now we have that that's equal to the limit due to our improper integral as n approaches infinity of the integral from 0 to n of e to the negative st cosine of bt dt. And now we have that that's equal to the limit as n approaches infinity. And here we are going to be using table. So I'll go ahead and put that right there. And using your table, you will come up with e to the negative st, and in the numerator we have negative s cosine of bt plus b sine of bt. And then that's divided by s squared plus b squared. And we will evaluate that from 0 to n. So plugging in our n for our t's, we have e to the negative sn multiplied by negative s cosine of bn plus b sine of bn, all divided by s squared plus b squared minus, we will have a negative s here, plugging in a 0. You can see we will have just that negative s remaining, divided by s squared plus b squared. And we have s over s squared plus b squared. Okay, let's take a look at the next one. Determine the Laplace transform of the function f of t equals e to the 2t cosine of 3t. Did want to mention here, of course, this is for s greater than 0. And here, though, we would have to remember that the domain of the Laplace transform is all the values of s for which this integral exists. And here, this integral would only exist, this integral would only exist for s greater than 3. So we did need to include this for s greater than 3. Okay, so let's go back to our example. So we are trying to find the Laplace transform for e to the 2t cosine of 3t of s, and that's by definition the integral from 0 to infinity of e to the negative st e to the 2t cosine of 3t dt, and that's equal to the integral from 0 to infinity. And let's go ahead and combine those exponents. Cosine of 3t dt, and that's equal to the limit as n approaches infinity of the integral from 0 to n of e to the 2 minus s t power cosine of 3t dt. And for that integral, of course, you will use your tables. And here we have e to the 2 minus s times t power multiplied by 2 minus s cosine of 3t plus 3 sine of 3t, all divided by 2 minus s squared plus 9. And we will evaluate that from 0 to n. So now we have the limit as n approaches infinity of e to the 2 minus s multiplied by n, 2 minus s cosine of 3n plus 3 sine of 3n all divided by 2 minus s squared plus 9 minus, we're plugging in a 0 now, and of course we're just left with 2 minus s. So now if we take the limit as n goes to infinity, we lose this entire first term due to this negative infinity power. And we are left with the opposite of 2 minus s over 2 minus s squared plus 9, which is equal to s minus 2 over 2 minus s squared. And we can go ahead and write that as s minus 2 squared plus 9. Okay, let's look at our next example. Again, we're looking to determine the Laplace transform of this function, e to the negative t sine of 2t. So we will have the Laplace transform of e to the negative t sine of 2t of s, and that's equal to the integral from 0 to infinity of e to the negative st, of course multiplied by our f of t, and we will come up with 0 to infinity. That integral e, combining those exponents, we could go ahead and take that negative out and put an s plus 1 times t, sine of 2t dt. So that is equal to the limit as n approaches infinity of the integral from 0 to n of e to the negative s plus 1t sine of 2t dt. And again, you will use your table integration to come up with that integral. And we have e to the negative s plus 1 times t power multiplied by negative s plus 1 sine of 2t minus 2 cosine of 2t all divided by s plus 1 squared plus 4. So this looks a little familiar after working the previous problem. And here, if we go ahead and plug n in, of course, we still will have to take the limit afterwards. So we have e to the negative s plus 1 multiplied by n, negative s plus 1 multiplied by the sine of 2n minus 2 cosine 2n, all divided by s plus 1 squared plus 4. And now subtracting, plugging 0 in, you can see that we will have a negative 2 right here. So we could just put a plus 2 divided by that same denominator, s plus 1 squared plus 4. And when we take our limit as n approaches infinity, of course, this all goes to 0. So we have 2 divided by s plus 1 squared plus 4. Okay, and now let's look at this piecewise defined function here in our next example. I did want to mention here we would have to have for s greater than negative 1. And in this previous example, this would have to be for s greater than 2. Okay. Since the Laplace transform is for defined on 0 to infinity for f of t, and then of course we have to use the domain of the function in that integral. Okay, maybe I'll just highlight those. No limitations there. And we had for s greater than 0 here. Okay, so let's continue on with our piecewise defined function. And here we will split the integral. Okay, so we have the Laplace transform of f of t of s. And we're going to have that integral from 0 to infinity of e to the negative st multiplied by our f of t dt. Now here is where we're going to split that integral. We're going to say that that's the integral from 0 to 1 of e to the negative st f of t dt. And actually, we can put from 0 to 1, this is our function, 1 minus t dt. And now we will add that to the integral from 1 to infinity of e to the negative st. And that's going to be multiplied by 0 dt. And as you can see, we end up with the integral from 0 to 1 of e to the negative st multiplied by 1 minus t dt. And that is equal to, and we will do a little table integration here. So we have 1 minus t, negative 1 and 0. And then we have e to the negative st, negative 1 over s e to the negative st. And then we have a 1 over s squared e to the negative st. And so now that integral will be a negative 1 minus t all over s multiplied by e to the negative st power. And then we have a minus 1 over s squared e to the negative st. And we will be evaluating all of that from 0 to 1. Okay. And plugging in a 1, of course, we lose this term, and we would have e to the negative s over s squared minus, and then plugging in a 0, we'd have minus, a minus, and we would have 1 over s, and we'd still have our minus 1 over s squared. So I could actually fix that here real quick. So that would be minus negative 1 over s plus 1 over s squared. And then we come up with e to the negative s over s squared plus 1 over s minus 1 over s squared. And of course, this is for s not equal to 0. Okay, let's take a look at the linearity of this Laplace transform. So let f1 and f2 be functions whose Laplace transforms exist for s greater than alpha, and let c be a constant. Then for s greater than alpha, the Laplace transform of the sum of f1 and f2 is equal to the sum of the Laplace transforms. In addition, we have that the Laplace transform of a constant multiplied by a function is a constant multiplied by that Laplace transform. So this property of linearity is very, very important. What we realize here is that the Laplace transform is a linear operator. Okay, and now let's take a look at this table over to the right. And some of these should look very familiar because we actually came up with some of these in the previous examples. Now, these are the Laplace transforms of some of the elementary functions. And we will be very familiar with these after working a few problems. And these do come up quite often when we solve linear differential equations with constant coefficients. So let's take a look at this example. Use the Laplace transform table, which was right there, and the linearity theorem to determine the Laplace transform of this given function. So let's go ahead and write that down. The Laplace transform of 6e to the negative 3t minus t squared plus 2t minus 8 of s is going to be equal to, and we're going to say by linearity, we have that that's equal to 6 multiplied by the Laplace transform of e to the negative 3t of s minus the Laplace transform of t squared of s. And I think I'm going to go ahead and write that below. And that way I can write a little bit larger. Plus 2 multiplied by the Laplace transform of t of s minus 8 multiplied by the Laplace transform of 1 of s. Okay, let me just fix that. Looks okay. What I might do is write some of these from the table right below these. So this Laplace transform here from our table, let me redo that. 1 divided by s minus a negative 3. Of course, that's 1 over s plus 3. Our Laplace transform of, and this, of course, is going to be for s greater than negative 3. And then our next Laplace transform, using our table, we have that this is equal to, for the Laplace transform of t squared, 2 factorial divided by s raised to the 2 plus 1 power. And of course, we're going to get 2 over s cubed. And then we have the Laplace transform of t, and that is going to be 1 factorial over s raised to the 1 plus 1 power, and we have 1 over s squared. And then the Laplace transform of 1 of s is 1 over s. And of course here we have to have s greater than 0 for these transforms here. Okay, so now using those, it was nice just to have those under there. We can put these together and we can say that that's equal to 6 multiplied by 1 over s plus 3 minus 2 over s cubed plus 2 over s squared minus 8 over s. And I could just put this 6 over the s plus 3 here. And then just keep these others just like this. Okay, and so this would have to be valid. Let me make a note here. For both, or the intersection of these sets. So therefore, S must be greater than 0. Okay, let's go ahead and use the table again and linearity theorem or property of the Laplace transform to determine the Laplace transform of this function. So here we have that the Laplace, the Laplace transform of e to the 3t sine of 6t minus t cubed plus e to the t is equal to the Laplace transform of e to the 3t sine of 6t of s minus the Laplace transform of t cubed of s plus the Laplace transform of e to the t of s. Now we will find all of these in our table. So that is going to be equal to 6 divided by s minus 3 squared plus 6 squared. And you can see this right here. Okay. And continuing on, then we'll have minus 3 over, that's 3 factorial, over s to the 3 plus 1 power. And then we have plus 1 over s minus 1. So putting this all together, we have that this is equal to 6 divided by s minus 3 all squared plus 36 minus 6 over s to the 4th power plus 1 over s minus 1. And of course, this is valid for s greater than 3. Okay, let's try another example. Use the Laplace transform table and the linearity of the Laplace transform to determine the Laplace transform of this function. So what we have here is that the Laplace transform of t to the 4th, e to the 5t minus e to the t cosine of root 7 multiplied by t, and I think I put that, should have put this of s here, is going to be equal to, and now let's use our principle, a linearity principle, t to the 4th, e to the 5t of s minus the Laplace transform of e to the t cosine root 7 multiplied by t of s. So we have this in our table, and here we have 4 factorial over s minus 5 to the 4 plus 1 power minus s minus 1, and you can refer to the table, divided by s minus 1 squared plus root 7 squared. So as you can see, this will simplify to 24 over s minus 5 to the 5th power minus s minus 1, all divided by s minus 1 squared plus 7. Okay, and of course this will be valid for s greater than 5 because we have to have the intersection of both of those domains. Okay,